So it's my privilege to introduce my close friend and colleague, Dr. Rogers F. Silva. He received his Bachelor's of Science degree in Electrical Engineering from Catholic University, Porto Alegre, Brazil, and his Master's in Computer Engineering with a minor in Statistics and Mathematics, and his PhD in Computer Engineering from the University of New Mexico with honors. Dr. Silva has also developed several client-centric tools and processes using machine learning and statistical analysis as a data scientist with Datalytic Solutions. But here, he's a multidisciplinary research scientist at Trend Center, interested in several topics, including deep statistical and machine learning, image analysis, and distributed analysis of big multimodal multi-subject neuroimaging data. And today he's going to be presenting the Landscape of Subspace Estimation, a unifying view, and the BSI subspace section. So Dr. Silva, if you don't mind, you have the floor.
Thank you so much, Thomas. Can you guys hear me well? Thomas, do you hear me well?
Can hear you quite well.
Good. All right. So thank you so much for the introduction, Thomas, and thanks to Dr. Calhoun and Armin Raji for setting up the BrainSpace initiative. So as Thomas mentioned, I'm going to be talking about subspace estimation today and push forward unifying view of the field and how that relates to the BSI subspace section. So the first part of the talk is going to be about the principles of subspace estimation and how that will help us map and navigate the landscape of methods. And part two of the talk is going to be bringing home the purpose and the goals of the BSI subspace section, in particular within the BrainSpace initiative. We're going to be talking about its vision, its activities coming forward, and as Thomas mentioned at the beginning, some new opportunities for students to participate and help with the student core. So the first part of the talk is then the landscape of subspace estimation, and start with some basic principles of source estimation, particularly a systems view of how data is analyzed. Usually we start with data and we want to do something to that data. And as a result of that, we might get compressed representation or some embedding. Depending on the approach we use, we might be interested or able to recover the primordial elements that originated the data in the first place. And these could be named different ways across the literature. Could be sources, dictionary items, latence factors, and etc. The fact that we are recovering primordial elements or even talking about them implies that this transformation that we want to apply to the data is actually an inversion of a generative model that took the primordial elements in the first place and generated the data from there. And possibly with some interference from noise at some point, which gives us this notion that there are true primordial elements and there is our best estimation of them. The main takeaway from here is that as we assess the properties or define the properties of this generative system, they determine how we're going to be able to, or whether we're going to be able to handle this inverting system. And particularly in blind source separation, the true primordial elements, the sources, and the generative function that transforms them into the data are both unknown. And that is the definition, the very definition of a blinded estimation. So even though we don't know those primordial elements and the generative function, we're still aware or able to choose what are the properties of these two elements in the system view. So it is exactly those properties that limit the types of function and sources that can be fit to the data. And as a result of that, it restricts the set of inverting systems that we can optimize for. And that's the cornerstone of how we go about estimating sources. So we've been talking about properties of sources and system and generative systems. So what are some examples of desirable properties for sources? The literature is filled with examples of that. I'll just outline some here. We might be interested in source sparsity, uncorrelated sources, or even independent sources. We might be interested in sources that violate or do not follow IID assumptions. For example, sources that have sample dependence, like autocorrelated time series, or even non-stationary sources. For example, spatial maps that have different mean activation depending on location. And there is a whole set of other interesting properties we might be looking at, like similarity to a prior, smoothness, linkage between sources, distribution form, non-negativity, and so on. And with respect to the generative system and its functional form, there are another interesting set of interesting properties we might be looking into, like linear versus nonlinear mappings, invertible mappings, different types of architecture, such as fully connected layers versus, say, a structured type of architecture like that of tensors, orthogonality. We might also optimize for sparsity and so on. The key point is that the choices really depend on the experimenter goals and the type of data. And today, my goal is to provide you with a set of tools that you could use to navigate the space of subspace models and make well-informed choices about which ones are appropriate to your needs. And if you're a developer, help you understand what are the relationships between methods that are available out there and what are the advantages of perhaps combining methods, what are the complementary advantages of each one, and possibly develop new methods. So in order to do that, it's useful to think of the following extensions. The first one is a very popular, let's say, not approach, but desire or understanding in the field, that if you have more data sets, intuitively you should be able to leverage joint information from these multiple data sets to more easily or more accurately recover these underlying sources from the data sets. And in the literature, there is just a lot of examples of that very type of generalization. They are usually named multi-data set, multi-view, multi-set, multimodal. There's a whole set of combinations that are actually an evidence that it's a very popular and desirable thing to have. And in terms of another interesting aspect, and this one is very, I wouldn't say unpopular, but not well understood or even known in the literature, which is the concept of multidimensional sources or subspaces. And the idea is that rather than estimating unidimensional or one-dimensional sources, you can actually estimate collections of sources, such that, for example, in methods like ICA, independent component analysis, your sources are not all independent, but rather groups of sources, subspaces, are. And within those subspaces, sources might not be independent. And this, I think, is a very interesting perspective, because it addresses a long-standing question that for many years I've heard of people who come into independent component analysis, first hear about it and then wonder, what if my data doesn't have independent components, or what if not all of them are independent? And these type of methods that do estimate subspaces are exactly the answer to that question. And the second point, and I think the biggest motivation for subspaces, is really that they represent high dimensional features that have a very powerful, very high representation power. I think of the example, a very good example of subcomponents within a network. So the components might be, the subcomponents might be expressed differently across populations and not independent of each other, just expressed differently. So it would be very desirable to be able to estimate such high dimensional features that have the ability now to be non-static and actually change with the population you're studying, and still provide you a grounding connection across populations. So just to be clear here on this representation in the right-hand side, if you can see my laser pointer here, I'm representing subspaces as sources with the same color. That's just a pictorial representation to push across the idea of subspaces, that they are higher dimensional representations. So once we have that idea in mind of those two concepts, we can start looking at the types of problems and realize that there is a natural hierarchy of problems. That we can look at. To begin with, the basic approach is, or the basic type of problem is that of analyzing a single data set with unidimensional sources, and this is the case here of SDU methods. And an extension of that is very naturally that we will analyze multiple data sets simultaneously and learn linked sources. These sources, even though they're linked, they're still unidimensional within each data set. And this is a very interesting area of research that's still under development, but with very exciting results. Another extension that we might think of is, like I mentioned before, back to a single data set, but now with sources being decomposed into subspaces or grouped together into subspaces. And the more general case, of course, when we simply allow subspaces to occur naturally within each data set, or maybe even be absent for some data sets, have different dimensionality, perhaps across data sets, and be linked across these data sets. Quite obviously, this is a much harder problem to solve, but it highlights that this perspective has an implicit hierarchy of subproblems within it that is worth for understanding and for developing new methods. Another perspective on the field that's primarily been pushed by Dr. Adali, Dr. Tule Adali, is the multidiversity perspective. I call it the triad. And the basic definition of diversity is essentially all of the properties that I had been discussing since the beginning, but with a very important underpinning, which is that the impact that they have on the uniqueness of the solutions get from blind source separation methods. And so the idea is to group these properties into different classes of diversity. The first one here is multi-data set diversity, and it refers specifically to those instances where we're combining multiple data sets with an intent to establish hard linkage between them, which occurs anytime you do concatenation on the data sets, or when you construct tensors with the data sets. And it's an interesting observation that in the case of tensors, the more data sets or views that you have, meaning the higher order the tensor, the more uniquely identifiable the sources are. I'm sorry, the more sources are uniquely identifiable. So you're able to identify more sources. And that's very interesting because the two ideas, items B and C here, they can be even combined together by concatenation of tensors and matrices, which establishes then that you could leverage tensors on one end and their high dimensionality to attain uniqueness, and because of hard linkage through concatenation, extend that to matrices. So very interesting idea. The other point is then to look at the statistical diversity as another class of diversity, which is basically all the different ways that statistics can be used to assess the connections between sources, which here is highlighted as soft linkage, and also to assess whether there is dependence within your samples, or if your distributions are changing, say over time or over different points in space. In summary, whether your sources are IID or not. At the same time, we can look at another set of diversity options, property options, and these are then characterize constraints that you can apply to regularize or improve the identifiability or the uniqueness of different methods. And I'll stop here, Thomas, to take any questions if there are any at this point.
So there aren't any questions at this point, so feel free to raise your hand using the emote button if you'd like to ask anything to Dr. Silva directly. Otherwise, you can feel free to type it in the Q&A section. Is there anything you'd like to elaborate on while we're waiting?
Well, just that the point up until this point is that there is this concept of multidiversity, which is the idea of combining different properties into sources and generative systems to make your solutions more unique, the set of solutions. So for example, it is possible with, and that's known for, say, independent component analysis, that sources have to be non-Gaussian to be estimated with ICA. And the key characteristic of non-Gaussianity is looking at higher order moments or cumulants of the data. However, even with second order statistics, it is possible to estimate sources in ICA, which means we're using only second order moments and still. Yeah.
If I may interrupt you for a second, a quick clarification by Carlos Mendoza. By unique, do you mean independent?
No, unique doesn't mean independent. Unique means that there is no ambiguity in the data. It means that there is no other solution, that you have achieved the set of solutions that are all equivalent. For example, in principal component analysis, there is only one direction that has the maximal variance. There is an ambiguity whether the basis points, say, in one direction or 180 degrees from that. But generally speaking, uniqueness is guaranteed, regardless of whether you flip the sign of the principal components or not. So that's the definition of uniqueness. There's only one direction, and no other direction is going to have higher variance. In the case of principal component analysis.
Okay, are there any other questions? Okay, so we've got one from Armin. How feasible is it to use these complex techniques to study the brain? And on top of that, also how reliable are they considering the limited data existence in brain imaging?
So in terms of reliability, first, it's more about the number of samples. So yes, depending on the scenario at hand, maybe you don't have a lot of subjects and you're trying to combine multimodal data. There is a limit in terms of how much you can do if you want to do subspace estimation, particularly on those settings. There is a limit on how many subjects you need to have. But this is also not entirely known. Why? Because it also depends on how many types of diversity you have built into your method. This is like saying, I can look at the data in different ways, and each different way that I look at the data gives me additional information. So I'm not only looking for independent subspaces, but I'm also looking for subspaces that are non-stationary. And so if I look for non-stationary in the data, that gives me additional information to extract sources. So the true answer is there are limits, but the limits are not well known and understood. And currently we're seeing studies with a higher number of subjects. Take the UK Biobank data set. There are thousands of subjects, and in those settings, it is very feasible to use these methods. What was the first part of the question, Thomas?
Yes, sorry.
The first part of the question.
Minor UI issue. The first part of the question is how feasible is it to study the brain, but it looks like the question was answered.
Yes.
But
I think we can get going now, just to keep track. All right, so I'm going to move on now to the part where we actually start mapping this landscape of methods. And to do that, this is the tool I mentioned I was going to provide you with. And basically, it's a visualization tool. Like, how do we come up with descriptive boundaries? And two of those are pretty obvious from the beginning of the talk, when I was talking about methods that assess, that are able to simultaneously optimize, process, analyze multiple data sets, or that are restricted to single data sets. And also, on the other direction here, looking at methods that can estimate multidimensional sources within data sets or not. Another dimension that we can look at is the statistical links. This is the soft links that I mentioned initially, and what type of statistics they use or they rely on to establish this linkage. And just from those three types of properties, we can start to quickly label things around and put these different methods that I'm indicating here at the bottom into each one of these bins. I'm going to then discuss each one of these methods in detail later. But for now, let me propose an extension of that visualization by adding two more properties, sample dependence and non-stationarity, the green and the purple arrows here. And so with this, we're able to simultaneously visualize how methods map into this quote unquote 5-dimensional space, call it that way. This is the landscape. So how do we use this tool to navigate the landscape? First, we look at some of the simpler methods, those that analyze a single data set and extract unidimensional sources. There are three examples here, classical ones: principal component analysis, independent component analysis, and second-order blind identification. And the key point here is that if you look at principal component analysis, it is optimizing for uncorrelated sources using second-order statistics. Second-order statistics, whenever I say that, it basically means it's using the covariance information or the correlation information from the covariance matrix. Independent component analysis, on the other hand, is using all order statistics, meaning it's not only uncorrelating the sources, it's also making them independent. It's looking at higher order moments of the data, of sources against sources, the same way you build a covariance matrix, but now looking at higher moments. And so we can then make the same evaluation for second order blind identification and see that, yes, like PCA, it's using second order statistics, but differently from any of the other two methods, it is actually using sample dependence. It's assuming that your sources are autocorrelated time series, and it's leveraging that dependence between samples to pursue the decomposition or the estimation of the sources. And so with that information from those 5 different properties, we can map this on this upper left corner, ICA and PCA. And these are the methods that don't leverage non-stationarity and don't leverage sample dependence. They assume stationarity and independence between samples. And second order blind identification then is the one method here so far that leverages sample dependence for identification. And the color coding follows that legend over here. And moving on to methods that actually estimate subspaces from a single data set. Here I included 3 of them: multidimensional ICA, independent subspace analysis, and stationary subspace analysis. And right away, we see that multidimensional ICA is very much similar to SOBI in the sense that it also uses second order statistics and sample dependence to estimate the sources. The key difference is that it's able to recover dependent sources and allocate them to the same subspace. Then for independent subspace analysis, the key point is that subspaces are defined based on their joint distribution alone using all order statistics. And stationary subspace analysis is a very peculiar method that actually uses both the first and the second order moments, basically the mean and the covariance, to assess non-stationarity in the data. And that way it separates stationary subspaces from non-stationary subspaces. And following this same structure, we can map these methods here: multi-data set ICA, independent subspace analysis, and stationary subspace analysis. This end of the right-hand side of the slide here is for methods that leverage non-stationarity. And then very quickly, we have here a very well-known class of problems that use hard linkage, meaning that assume that all data sets share the same sources in this case. The first example is group principal component analysis, group independent component analysis, and probabilistic ICA. So like before, the method relying on PCA is just using second order statistics for uncorrelated sources. Group ICA is using all order statistics for independence. And probabilistic ICA is operating pretty much in the same way as group ICA, except it's using a different method for dimensionality reduction. It's the factor analysis with a Gaussian model. Now, because these 3 methods rely heavily on the concatenation of data sets and effectively treats the entire data set as a single large data set, very large data set, I consider it somewhat like borderline between a multi-data set method and a single data set method, because the way it actually decomposes the data is pretty much the same as a single data set method. It just operates on the concatenated data. And moving forward, a method for tensor decomposition that also relies on hard linkage. In this case, both the sources and the mixing coefficients are hard linked, meaning they are identical across data sets. And the only thing that differs across data sets are the sets of, could call it weights, that determine the extent to which these sources and loadings are expressed in the data. This is also relying on all other statistics because it's using probabilistic ICA to estimate the sources, and it's using parallel factors with the fixed set of sources estimated from probabilistic ICA to then infer the other elements of these matrices. So because it's actually using a tensor model to model all data sets together, I considered it like a more pure multi-data set model and place it here in the map. Thomas, are there any questions about these methods?
So we have one question from Enrique. I'm going to go ahead and let Enrico ask it himself to make sure that I'm following this correctly.
Thank you.
Yeah. Can you hear me?
Yes, I can hear you.
Yes. As I write in the Q&A section, the disclaimer is that as a clinician, all these subsets are very challenging for me. So the question can sound very naive. I mean, if I have a multi-site data set, for example, fMRI, but also structural data like BBM or contact thickness with no specific prior harmonization, how can I consider or take into account all these complex methods or approach to increase the utilization of different data sets, because it's a real practical and urgent point in clinical activity and also in neurological or psychiatric disease. So we have a significant number of data sets from different sites that is not so clear how to combine together. At the moment, the basic approach is to combine all the data set and to use a covariate of site, but it's quite a rude approach in my opinion. But there is, your presentation is very interesting from this point of view.
Right. Thank you. So yeah, there's some caution to take here. If I understand your question, the point is that you have multiple modalities, say VDM and fMRI.
Yeah, multiple modalities, but also multiple data set from different sites.
Yes. So within each site, you have all modalities available. It's just different subjects, right?
Yeah.
Okay.
Absolutely.
So so that is an example of a non-stationarity. I would be my first intuition, right? That the distributions, because of site differences, are going to be different across sites.
Yes.
At the same time, there are many methods, but there are methods that take that into account and actually leverage that kind of information to help in the subspace estimation. And when I say subspace, the special case of sources is also included. So even if we're talking about just simple ICA, it applies to that as well. So as long as you have a method that can take advantage of those peculiarities in the data, you can at least attempt to see if it's possible to analyze those data sets. Combining data sets across sites is definitely an important question to tackle. I think there is a role for subspace estimation in that setting, and I don't think it's been explored enough yet. I will not say that the methods are out there to take full advantage of the peculiarities of this scenario, but there is already something that can be done as a first try, I think. Yeah.
Okay, thank you. Really interesting.
Mm-hmm. Thank you.
So we've got another clarification from Carlos Mendoza for tensor-based ICA. What do you mean when you say built-in scale compensation?
Mm-hmm. So what I mean is that, we quickly go back here. What I mean is that when you fit the parallel factors model, it automatically learns these diagonal elements here that are just scalar values. And these scalar values will be optimally they will be optimal in the sense that they will reflect the extent to which sources are represented in the data set. That's what I mean by built in. It's built into the parallel factors model. And in contrast, consider group PCA, for example, that you estimate group sources, and you can then, after the fact, apply back reconstruction, meaning after the estimation is done, you can apply back reconstruction in a separate post hoc step to recover the sources, to recover data set specific sources that won't be necessarily identical across data sets, probably not. So that's the contrast. It is still possible with a model that estimates identical sources across data sets to recover data set specific sources, but you need post hoc compensation, and the compensation is built into Tensor ICA. That's what I meant. So Thomas, in the interest of time, I think we should move on with the talk.
Yes, please do.
All right, so the next set of examples that I have here include methods that leverage soft linkage. And soft linkage is the notion that sources are estimated separately for each data set, but the decomposition happens simultaneously in such a way that there is statistical linkage across corresponding sources. And examples of these methods include canonical correlation analysis, multiset or multimodal, in which case it's leveraging second-order statistics via maximization of the correlations. This is correlations across corresponding components, and all other cross correlations between components within and across data sets are set to 0. The same with partial least squares, where you're maximizing covariance instead of correlation. And that's only saying that variance plays a role in the decomposition, whereas in canonical correlation analysis, all the data sets are implicitly normalized, and scales and variances don't affect the decomposition. The last example is independent vector analysis, where the associations across data sets happen using all order statistics. So this is using higher order moments. And therefore, you attain independence within data sets and general dependence, which includes, in the general case, linear correlation dependence as well. But it might include, say, correlation between variances and so on. More general types of dependence can be captured. So since this is a very principled approach, there are no hard links implicit here. I place these two methods out there on that end of the spectrum. I'm assuming for this particular example that these methods are not using any sample dependence or non-stationarity. That's why I'm mapping them on this end of the map. And I think this is the last, or one before the last, set of examples. Now using hard linkage on the mixing coefficients instead. And these methods are common spatial patterns and joint independent component analysis. One uses second-order statistics, the other one all-order statistics, but applied to a weighted average of the distributions across data sets. I then map these two out here because the sources are estimated separately for each. You still get sources for each modality or for each data set separately, and they're not hard linked. It's only the transformation that is hard linked. So I map them somewhere in between these approaches and IVA and CCA. Linked ICA is another example where it's kind of combining tensor ICA on groups of data sets that have some commonality between them, have the same data type. So each data type has its own tensor ICA decomposition, but all of them, like joint ICA, like a joint ICA model, they all have a shared hard link on the mixing coefficients. So like joint ICA, it's also applying all other statistics on the weighted average of the source distributions. And so I place this method right here next to joint ICA. And I think this is the last one, yes. These are the two more general methods that can estimate subspaces from multiple data sets. First one is joint ISA, and the second one is multi-data set ISA. And the key difference is that joint ISA is using second-order statistics as well as sample dependence and non-stationarity, depending on how we set up the problem. Whereas multi-data set ISA is relying only on, it's relying on all other statistics, but it's not relying on sample independence and non-stationarity to recover these decompositions. And for that reason, I indicated MESA on the top here and joint ISA on this corner, quite by itself here as the only method that's leveraging at the same time non-stationarity and sample dependence. So Thomas, I think I'll skip this set of questions just in the interest of time. And there's going to be another stop before the end, and I can take questions then. So very quickly, what else is out there? So like I mentioned in the beginning, there are other ways to go at this and understand how methods relate to each other. And that's just a matter of picking your favorite or most interesting property from that initial list and looking at those methods that implement them. For example, incorporating prior information, that's something that is becoming very popular and showing very interesting results lately. There's the concept of joint and individual decompositions that are a very small, let's call it, extension of IVA that allow for certain sources to be absent in some data sets. Recently, we had, I guess, in the past 5 years or so, maybe less, some very, very interesting breakthroughs in nonlinear ICA and nonlinear blind source separation in general using deep contrastive learning. We're going to have a talk this Friday. I highly recommend everybody to come see it with Apo Hivarinen, the creator of FastICA. He's going to be talking about this. And lastly, but not least, sparse representations. And there's so much more that we could go on forever here. The point is that with this perspective that I've presented here today, you should be able to go after the things that are interesting and relevant to the questions you're trying to answer in your particular research and have more confidence on the choices you're making for solving those problems. And this is just illustrating that indeed there is interest on those things. People value the use of deep feature representations in their neuroimaging research. People are interested in exploring multi-data set analysis in their next neuroimaging project, and people seem interested in learning more about subspace modeling. So it only goes to confirm that this is a very interesting area of research, and there's a lot of interest from the community. To conclude this first part, then here are some final remarks. The simultaneous utilization of multidiversity gives any method the ability to leverage different aspects of the data to more easily and more uniquely identify sources and subspaces. Subspaces particularly have the ability, natural ability, to increase representation power for very complex features, which are common in our current state of the data that is becoming just more complex. And there's still a lot of things that are left to do for subspace estimation. There are many gaps, as you notice in that map. It's not a complete map, of course, but it is a representation that indicates there's more to be done, maybe more methods to be created or combinations of methods to be explored to leverage different qualities of each method. Moving forward, I think there's going to be a discussion, and a relevant one, about whether subspaces are as valuable or more or less or complementary to nonlinear features. And then the idea is that both of these types of features are useful to represent complex behavior and complex features, so complex characteristics of the data. And then there is a question, is there value in combining these two, or are they mutually exclusive? And like I mentioned, the data is getting ever more complex, high resolution. We have simultaneous studies being done, different modalities. And the nature of fMRI data and any MRI data is complex valued. And I didn't touch on anything here today, but there are methods for source estimation that work directly on complex value data. And there is value in exploring those directions as well. And the bottom line is, in the end of the day, there are trade-offs. And as a researcher, we need to be well educated about what things make sense to try for the problems that we have and take those trade-offs into account. I hope that this will help you identify those trade-offs. So quickly moving on to the last part of the talk. I'm a little over by a minute, but I'll try to be quick here. So the PSI subspace section is a part of the BrainSpace initiative. And the BrainSpace initiative has this vision of being a collaborative environment, learning environment, with equal opportunity resources for brain research. And building on that vision, we, in the PSI subspace section, want to explore the landscape of multivariate and subspace analysis methods like we did today, and with a special focus on understanding how these methods relate to each other, both new and classical methods that we would like to study. And we also see it as, have a vision that it should be a safe environment for encouraging participation at all levels, from naive questions, there really is no naive question, to actually very technical questions. We're looking forward to have debates, to share relevant papers with each other, to start new collaborations. And this is definitely not a place for just communication between participants and us. There is no us in the sense of me and Armin and Dr. Calhoun, but rather it's a community. And we're hoping that you will find this resource useful to find new friends with similar interests and start new collaborations from there. And the way that we're trying to stimulate those kinds of interactions is by having these talks like today. We're planning to have these talks maybe once or twice per month. We'll be inviting experts to discuss their research and spend some time in our Slack channel answering questions and interacting with the members of the BSI. We'll be discussing papers. We're looking forward to this. We're going to experiment with a more collaborative format. There's going to be information about that sent later on. And just to give you a heads up, this is the next talk. It's going to happen Wednesday, next week, June 2nd at 10 a.m. Eastern Time. That's going to be around 5 or 6 in the evening in France, if I'm not mistaken. So if you are interested, come take a look. Pierre Heblan is going to be talking about noisy independent component analysis for brain signal processing, challenges and opportunities. Pierre has done some really interesting work on a range of blind source separation applications, including faster ICA and what was the other one? Multi-view ICA. So I think he's going to be talking about those things in his latest work in spectral ICA. We're also going to have later next month, at the end of the month, Donna Lahat. She is the developer of Joint ISA, and she's going to be talking about that and her latest work on combining or the relationships between Joint ISA and tensorial decompositions. A reminder again that this week we have a talk coming up on Friday about nonlinear independent component analysis. And to conclude, highlight to students that are here today that if you're interested, there are opportunities, and we're going to be sending out more details how you can apply to participate more actively in the student core of the BSI subspace section. You're going to be helping us brainstorm and prepare news and discussion bits that we're going to be sharing throughout the week. And later on, you can also have the option to help us organize new activities, including discussion panels with experts on a variety of topics to be defined. There are no real requirements except that you should be a student with an interest in the field and have some time to commit. And we're hoping that maybe an hour and a half a week will suffice. And this is a short-term assignment of 6 months. And if you're interested, there's going to be an option to extend it twice. Obviously, there's a benefit to students from helping us out. It's going to look great on your CVs. It's a great badge to have, service badge, that is. And it's going to be an opportunity to have a direct channel to experts and learn more about cutting-edge research. So finally, I'd like to thank Dr. Calhoun here at the Trend Center and Dr. Iraji for envisioning the Brain Space Initiative. I'd like also to thank the AAA Signal Processing Society and the mentorship of Dr. Talea Dali. And lastly, thank my good friend Thomas de Ramos for moderating this talk today. And thank you all for attending. Are there any final questions?
Thank you very much, Dr. Silva. We have one that's left over from Carlos. I see he's still here. I'm going to go ahead and unmute you, Carlos Mendoza. Would you like to ask it yourself about your EEG time series?
Yes, can you hear me?
Yes, I can hear you.
Hi, Doctor. Thanks for your talk.
Thank you.
I'm actually interested in joining the BSI initiative. So,
Nice.
yeah, just that I'm working with the ECOG data with neuro time series, and we are interested in finding like waveforms on that data, like patterns, oscillatory patterns. But sometimes those patterns have different lengths on time. They have different time scales. So I was wondering if among the methods that you have explored, there are methods that consider that the sources or the dictionary items have like different time scales.
Right. Well, the short answer to the question is maybe no, but the long version of the answer is that I think it is something manageable, because you could think of the length of these elements as maybe an expression of very different, an expression of non-stationarity in the distribution. I am not particularly familiar with a method that explores that kind of decomposition. But also, what I can say is there are many ways to look at the data. And I'm not exactly familiar with your application. But some things to consider, for example, are if you have knowledge of when trials occur, you could use trials as your samples and look at your data transposed and just stacked differently, rather than thinking of the entire time course with variable length sections. If you know how to chop the time series in its different lengths, maybe because you have knowledge of when the trials occurred, you can take those snippets, and even though they're different in length, I think it might be possible to analyze them if you transpose them and stack them, and analyze them over trials instead. But I'm just going off the cuff here. I'm not particularly familiar with those applications, so I will say that I think it's possible, but I would have to take this question offline, I think, to explore a little bit more the details. Does that answer your question? Is that good enough as an answer, or are there other questions, follow-up questions?
It's already spawned two sub dialects, I think. So that's a good question. We also have a few people requesting some of the slides of the talk. As we said, this will be recorded, but we can share the slides if it comes to that. One more I want to address before we wrap up from Monica Argwal. Could you go back to your landscape slide and give sort of a very, very brief description of what the quadrants represent?
Yes. So the upper left quadrant represents methods that do not leverage simple dependence or non-stationarity in the data, which means if your data is non-stationary, or if you have simple dependence like autocorrelation in time series, these methods will not take advantage of that, not going to be able to use that information to identify the sources. And likewise, the methods here on the right-hand side, they do leverage non-stationarity. And the methods in the bottom, they do leverage simple dependence. You can think of autocorrelation in time series. Yeah.
All right, thank you very much.
Thank you.
All right, thank you very much for your time, Dr. Silva. I think everyone enjoyed the talk. I hope you all have a lovely day.
All right, thank you so much, everyone, and have a good day.